Hello everyone, I am Assistant Professor Milan V. Patel. I am an Electrical Power System from the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Today we will discuss chapter number 6, Power Factor, from the subject Power Quality and Management, having a subject code 2180911 of the BE Semester 8 Electrical Engineering Department. So let's start with the power factor correction. So in simple term, power factor correction means a reduction of lagging reactive power Q or lagging reactive current IQ. So first of all, consider the figure in which source V supplies the resistive and inductive load with the impedance Z and the value of the impedance is R plus J omega L. So from this figure we can say that current I is equal to V by Z. Current I is equal to V by Z. This is simple Ohm's law. I is equal to V by Z. Now put the value of Z is equal to R plus J omega in this equation. So our equation will become V divided by R plus J omega L. R plus J omega L. And the apparent power S is given by VI. S is equal to VI. Now simple put the value of I from this equation so our apparent power S is now become V square divided by R plus J omega L. Now multiplying the numerator and denominator by R minus J omega L. So our equation for S now become V square divided by R plus J omega L into R minus J omega L divided by R minus J omega L. So now S is equal to V square into R minus J omega L divided by R square minus J square omega square L square. We know the value of J square is given by minus 1. So minus minus plus. So our equation will become V square R divided by R square plus omega L square minus J V square omega L divided by R square plus omega square L square. So now compare this equation S with this equation S is equal to P minus JQ. So from this equation, this term is P, active power, and this term is reactive power Q. So minus Q indicates that the reactive power is lagging, and plus Q in this equation indicates the power is leading. So from figure we can say the lagging. So this is the active power P, this is the apparent power S, this is the leading reactive power, because this is the leading power factor angle, and this is the lagging reactive power Q, this is the apparent power S. So these are the two difference between the leading and lagging reactive power. So now we can correct the power factor to unity. Unity means 1, means power factor is equal to 1. Again we know that tan phi is equal to Q by P. From this figure tan phi is equal to Q by P. So again we know that Q is given by, tan phi is also given by omega L by R. Omega L by R. This is from the power factor power triangle, and this is from the impedance triangle. Now this is omega 1 upon omega RC in terms of the capacitive resistive circuit. This is inductive resistive circuit. So we can say that phi is given by tan inverse omega L divided by R. Omega L divided by R. So now power factor is given by cos phi, and put the value of phi from this equation. So our equation for power factor is given by cos into tan inverse omega L by R. So this is the power factor correction equation. I hope you understood this one. Now let's take one example. So in figure V is equal to 480 volt, R is equal to 1 ohm, L is equal to 1 millihenry. So first find positive Q means reactive power for unity power factor. Find positive Q for 0.98 power factor. So this is the figure in which 480 volt is supply AC voltage, 1 ohm is the resistance load side, 1 millihenry is the inductance load side. Now from this value we can find the value of the inductive reactance. XL is equal to omega L is equal to 2 pi FL is equal to 2 pi, value of f is equal to 60 and L is equal to 1.0 into 10 raised to minus 3. This is the 10 raised to minus 3 for the millihenry. This is for millihenry. So our XL will be 0.377 ohm. The value for the inductive reactance is 0.377 ohm. So now first of all we have to calculate the active power P. Active power P, and the equation for the active power is V square R divided by R square plus omega square L square. Now put all the value in this equation. The value for V is equal to 480 volt, R is equal to 1 ohm, R square is equal to 1 square, omega square is equal to omega L square is equal to 0.377 in whole square is equal to 201.75 kilowatt. 201.75 kilowatt. So this is the active power which is obtained from this equation. Now same for reactive power, V square omega L divided by R square plus omega square L square. So put the value for V omega L R in this equation. So 480 whole square into 0.377 divided by 1 square plus 0.377 whole square. So the value for the reactive power is given by 76.06 kilovolt ampere reactive kVAR. So this is the reactive power for this particular figure of this example. Now we will find the power factor angle phi, and we know the equation for the power factor angle is given by tan inverse omega L by R. So omega L is equal to 0.377 divided by 1. So value for the power factor angle is 20.66 degree. 20.66 degree. So now power factor is given by cos phi means cos 20.66. So value for the power factor is 0.936. 0.936. Now to correct the power factor to unity, we need the leading kVAR of 76.06 kVAR. 76.06 kVAR, because these are the reactive component. So for making the power factor unity, we have to supply 76.06 kVAr in leading. So this is the leading kVAr required for the unity power factor. So now P is equal to 201.75 kilowatt. So now we have to find Q regarding 0.98 power factor. So cos phi is equal to 0.98. So phi is equal to 11.48. Phi is equal to 11.48 degree. So put this value in the equation of tan phi is equal to Q divided by P. Tan phi is equal to Q divided by P. So tan 11.48 is equal to Q divided by P. So put the value of P 201.75 into 10 raised to 3. So our value for Q is given by 0.203 multiplied by 201.75 into 10 raised to 3. So value for the QT2 is given by 40.97 kVAr required for the power factor of 0.98. So this is the Q required for 0.98 power factor. And also we know that the reactive power required for unity power factor is 76.06 kVAr. So leading kVAr required for the 0.98 power factor is given by Q1 minus Q2. Q1 minus Q2. So value of Q1 is equal to 76.06 and the value for the Q2 is 40.97. So 35.09 kVAr leading is required for the 0.98 power factor. So this is the answer for the question number 2 and this one 76.06 is the answer for the problem 1. So this is the example based on the power factor correction. Now important equations. Q1 is given by P tan phi 1 and Q2 is given by P tan phi 2. Then delta Q will be P in bracket tan phi 1 minus tan phi 2. So this is the important equation for the examples. Now Q1 is equal to S cos phi 1 and Q2 is equal to S cos phi 2. So delta Q is given by S in bracket cos phi 1 minus cos phi 2. Now another example, a 5 MVA transformer is loaded to 4.5 MVA at a power factor of 0.82 lagging. Calculate the leading kVAr necessary to correct the power factor to 0.95 lagging. If the transformer has a rated conductor loss equal to 1.0% of the transformer rating, calculate the energy saved assuming 24 hours operation at the operating load. Figure contains the power triangle of the given load and power factor conditions. So this is the figure based on our example. So in this figure we can see that this is the active power P common, this is the reactive power Q1 and corresponding apparent power is S1, and for this power triangle the power factor angle is phi 1. Now by supplying delta Q reactive power in leading form, the reactive power become lesser and its value is Q2 and corresponding value for the apparent power is S2. The P remain constant in both the cases and this is the phi 2 for the power factor angle for this Q2. So now existing power factor angle phi 1 is given by cos inverse 0.82. Cos inverse 0.82. So it is given by 34.9 degree. 34.9 degree. Now corresponding power factor angle phi 2 is given by cos inverse 0.95. Cos inverse 0.95. So 18.2 degree. 18.2 degree. So we find the power factor angle for the 0.82 and 0.95 power factor. So now Q1 is given by, we know the equation for Q is equal to S sine phi 1. S sine phi 1. So now put the value of S is equal to 4.5, sine phi 1 sine 34.9 is equal to 2.574 MVAR. So this is the Q1. This is the value of Q1, means this value Q1 is given by 2.574 MVAR. Now find the P regarding this. So it is given by S1 cos phi 1 is equal to 4.5 into cos 34.9. The value for the P is given by 3.69 megawatt. 3.69 megawatt. So this value of P is given by 3.69 megawatt. Now same procedure follow. Now we have to follow same procedure for this triangle. For this triangle Q2, S2 and P. So Q2 is given by P tan phi 2 is equal to 3.69 into tan 18.2, because now we have to consider this angle Q2 phi 2. So our value for Q2 is given by 1.214 MVAR. Now we have to find the difference between the Q1 and Q2 is given by delta Q. Delta Q is given by Q1 minus Q2, 2.574 minus 1.214. So value for the leading kVA required to improve power factor point from 0.82 to 0.95 is given by 1.362 MVAR, leading for power factor 0.80 to 0.95. For improving the power factor 0.80 to 0.95, we required the reactive power 0.362 MVAR in leading. Now find S2. S2 apparent power for the 0.95 power factor. So it is given by under root P square plus Q square. So under root 3.69 square plus 1.214 square is equal to 3.885 MVA. 3.885 MVA is the apparent power for the case number 2. Now power factor penalty. So typically electrical utilities charge a penalty for the power factor below 0.95. So 0.95 below power factor utilities are. So now the method of calculating the penalty depends on the utility. Now main two reasons for the low power factor penalties are, first one is increase in generation. So this is the figure for first case is Q1 is equal to 2.5 kVAR and corresponding S1 is equal to 4.5 MVA. And for this Q1 and S1, our active power is P is equal to 3.6 megawatt. Now we will improve our power factor and become the reactive power lesser from 2.5 to 1.2 kVAR. Now the power factor angle also reduces to 18 degree, and the S2 regarding this Q2 is 3.8 MVA, and it will supply the P is equal to 3.6 megawatt active power for this lesser generation or lesser apparent power. So by improving the reactive power or reducing the reactive power, we can supply more active power at same generation. Now second one is P is equal to root 3 Vi cos 5. This is the power equation, active power equation for the three phase. Now I is equal to P by root 3 V cos 5. The equation for the I is given by P by root 3 Vi cos 5. So as the cos phi decreases, as the power factor decreases, the value for current will be increases, and due to this decrease in the power factor, the value of current will increase, and due to this increase of the current value, the I square R loss increases. So this is the basic two reasons for the power factor penalty. This is the power factor penalty reasons. Now other advantages of the power factor corrections are, first one is reduce the heating in the equipment due to improved power factor, reducing the heating effect in the equipment. Second one is the increased equipment life. Third one is the reduction in the energy losses and the operating cost. Fourth one is the freeing of the available energy from the generation or apparent power. So more active power will be used from the apparent power. Fifth one is the reduction of voltage drop in the electrical systems. So these are the main advantages of the power factor correction. I hope you understood this theories and importance of the power factor. Thank you.